So hello everyone, this is lecture 17 for the classical physics. In the last lecture we have completed the gravitation part. From today onwards we will start the real physics actually, I will say that. So that is Lagrangian. So what is Lagrangian, what we will study in that? See, there is Newtonian mechanics and there is then Lagrangian and the Hamiltonian mechanics. So see, when there is a very simple system, means like a particle in a space or vacuum, when there is no external forces and a simple motion we are considering, means simple physics and the equation of motions we have studied, then we use a simple formula, then we can find the whole path equation. Okay, like you have simple acceleration, you can find the force, and y acceleration, z acceleration, the all components. You can find x, y, z because there are three equations, three variables, so you can find all the things. Means a simple physics that can be solved by Newtonian mechanics. But problems came when you are in a constant system, like when you came to in the real world. When you see that when particle is moving, then it will gonna see a lot kind of forces, and we don't know about that. Means we don't know the nature, actual nature of those forces. Like in pendulum, we have the damping forces. We just know that it is damping, but what is causing that damped motion, we don't know about it. And many dissipative forces and damping forces we have in the nature. So those are the constants. So when we study about them, that is Lagrangian. Means now let's see, we have constant to present. When there were three simple equations, we have three variables, it was easy to solve. Now constant force is present. Now ma will be this force plus that means constant force, and we don't know the true nature of this constant force. Now what you will, how you write these equations in this with the constant presence? You will write mx double dot equal to fx plus fx, fy plus fy, fz plus fz. Now we have these three more variables. So see, you have x, y, z and fx, fy, fz, six unknown things, and only three equations you have. So you can't find these six variables through the Newtonian mechanics. Means because you don't know the actual nature, that's why you can't know. But still, we don't say that the Newtonian mechanics fail here. For a simple system, means not very complex, we use some, means we guessed these constants, like we apply for the conservation of linear momentum, conservation of angular momentum, for the torque equation, conservation of energy. We apply these equations to find the dissipative forces, and actually we are able to solve some simple equations with the help of these constants, because these are also part of constants, and we know these things only. So that's why means these systems are easy when the constants are simple and equations are simple, or simple system is simple. So Newtonian mechanics works. But when the constant forces becomes complex very much, then it won't be easy to solve them and find these forces, okay, unknown forces. So that's why we have to introduce the Lagrangian and the Hamiltonian. So let's see what are they. With the help of Newtonian mechanics, it becomes difficult to solve a problem if constants are involved. This is so because the exact nature of constant forces is not known most of the time. To overcome this problem, two new methods or approaches were developed, which are called Lagrangian formulation and Hamiltonian formulation. These approaches are based on energies, not on force. The exact nature of the constant force is not required in these approaches. So these approaches, the Hamiltonian and the Lagrangian, involve the energy, not the force. So that's why we don't need the exact nature of force now. Okay, so we just substituted that thing with the energy. So we'll see how energy is now helping us with this problem. So this was the base why we have started this kind of things. So moving forward, first let me introduce you with the constants. What is the meaning of constant here? See, this is a billiard board, okay, and what happens in a billiard board? There are balls in that, and it's a pool type structure, and then you strike this ball, then it will gonna move something like this, okay, and the dimensions of this board is 2a from this here and 2b from here. Now what kind of restrictions you can apply on this ball, movement of this ball? So this movement of this ball will always between this a, if this is your origin, then it can't move from here to here, it can't move from here to here. It will be foul, means it will be restricted to go from here. So the restriction will be x will be minus a, greater than minus a and less than a, and y will be greater than minus b and less than b. So these are the constants applied here, and it can't move to the upper side, so z will be 0. So this is constant in this case. Now let's consider a simple pendulum. It's a wall and it's a long wire, or you can say any thread, string. So a bob is oscillating here. Now see, this oscillation is restricted in a plane. Only if we call this plane as xy plane and this is z axis upward, then this motion will be restricted in this xy plane only. So this is a constraint again. And we know that if it is stretched, completely stretched string, then this length will always remain constant. And in this xy plane you can find this length as x square plus y square. And if it is z component, then x square plus y square plus z square should be equal to L square. So this is a constant equation, and z equal to 0, so you can see that x square plus y square should be equal to L square. L is length, and where x is L cos theta and y is L sin theta, and z it can't move in this direction, so z will be 0. So these are the constant equations we applied here. So this kind of constants we get. Let's see one more thing. A spherical means it's a conical surface, and a particle is moving on this surface like this. So what kind of constant you can apply here? See, this is a part of a sphere, so you can apply the spherical coordinates here. What are spherical coordinates? These are in the r, theta, phi. R is this distance, theta is this angle made by in this direction, and phi is this angle. So you will study more in the mathematical physics lecture. You can see about the coordinate systems. Here I am just introducing this. So in spherical coordinates, so this angle will be alpha. So by introducing this, so this alpha will remain constant always. So this is a constant here. And in cylindrical system, how you can write this? So if then this distance will be s of cylinder, and it will be again, it will be phi, and theta will be here. So when you write it here, so you can write like x equal to s cos theta, y equal to s sin theta. You know theta is when this is place this line on this xy plane, then this will be theta. So you can write x and y in terms of theta. So these are the restrictions and the constant equations. In the Cartesian coordinate, you can write like this, means this will be here. So tan alpha will be s upon z in the cylindrical system, and in the Cartesian coordinates, this will be this s is nothing but under root x square plus y square from here and divided by z. So that's how you can write it. So these are the constant equations. Actually I am introducing constants here, so don't go into the coordinate system. Now see, there is also one kind of constants, like you have this sphere and you have air molecules inside. Okay, this is gas. Now they can't move outside this sphere. So what kind of constant here? So if this is our origin at center, and this is the position, it is at x, y, z, then this distance will be x minus 0 square, y minus 0 square, z minus 0 square. So x square, y square, z square will be always less than this r square, because particles here will be following equal to r square, here it will be less than equal to r square. So this will be constant equation for a gaseous system inside a spherical sphere. So this is again a constant equation. And there is one kind of constant also, like in a rigid system we know that distance between two particles doesn't change. So it will always, if this is 1, this is 2, then r12 will remain constant in any kind of motion. So this is a constant in a rigid system. So that's how we define the constants. I hope you get the point. What are constants? A motion that cannot proceed arbitrarily in any manner is called a constant. Means it can't move any manner, it can't move freely in any manner, it will be decided by some things. So that is called the constant motion. The conditions which restrict the motion of the system are called constants. So I hope this is clear to you. What are constants? Now the scalar equations that describe the surface of the constant are called constant equations. So these equations which we have described here for different systems are called the constant equations. And constants may be classified into two types. Now we have two types of constants. First is holonomic, second is non-holonomic constants. See, let me give you a brief idea. When the constant equations are definite, then you will call it holonomic. and when it is not definite, then you call it non-holonomic. Like in here, you don't know it will be minus a to a, anywhere between this range, anywhere between this range. So it is not definite. It involves inequality here. So you call it non-holonomic. Whereas in this pendulum, these are fixed. So this is a holonomic, example of holonomic. Here also it is an example of holonomic. It is non-holonomic because inequality, and it is not fixed, definite. It is not definite, means it can move anywhere inside. So I have just given you the brief examples. Now I will go in detail. So first is holonomic. If the condition of constants which is connecting coordinates with time can be extracted in form this. If the conditions, these means constant equations, can be represented in this form, means they involve only this x, y, z and t, means not more than these variables, only 3-4 variables you have, and not velocity and acceleration, all that things, then you call them holonomic constants. These constant is definite in nature and will reduce the requirement of independent variable to describe the motion of the system. What is the meaning of this line? Means one equation can reduce to the second, and the number of variables can be reduced from 3 to 2 and 2 to 1 to describe the motion. How? Let me tell you. If something is moving in a circle around this, then what is the equation of this circle? It will be x square plus y square equal to a square. This will follow this equation. Now see, this can't move in this direction. So it was first x square plus y square plus z square equal to a square. So z will be 0. So it is reduced to this equation. Now again you can put x square equal to a square minus y square. Sorry, y square equal to a square minus x square. Now y is depending on x. So it is again reduced by one variable. So now whole thing is depending on this x only, because with help x you can get y, and z is 0 again. So that's how you can reduce one equation to second and reduce the number of variables. That is only in the holonomic constants. And so this is the meaning of this equation. So this was the meaning of this statement. Variable to describe the motion of the system. Example. What is the example of holonomic systems? I already told you, simple pendulum. This one. Particle of mass moving in an inner surface of cone. So this was the system. And rigid body. In this rigid body also you have the definite constant equations. Now the holonomic constants are also, means you can define them in the integral holonomic constants also. Means how? You can represent this equation is also holonomic, because you can see that here you can involve dt, and then velocity component will be involved. Then still it can't be, it can be holonomic. How? If you integrate this equation, you will get this equation again, and this is holonomic because definite. It is definite. So sometimes you get equations in the form of differential and integrable also. So you can reduce them into this form. That's why they are called the integrable holonomic constants, reducible to holonomic. Okay. So sometimes you get this kind of things also. In these equations, velocity components etc. should not appear. So in holonomic constant equations, these x dot, y dot, z dot means velocity components, and r dot, theta dot should not appear. So those are the holonomic. Sometimes velocity component may be present in holonomic constant. However, they can be eliminated just by integration. This type of constants are called integral constants. So this was the example I told you. So they can be reduced to the holonomic constants or the integrable constants. Now what are non-holonomic constants? So the constants which are not holonomic are called non-holonomic constants, definitely. Which are not holonomic, they are non-holonomic. The equation of non-holonomic constant may be of two types. So I told you, which is not definite, these are non-holonomic constants. So this was the example of non-holonomic, and this was also the example. So what are the two types? It may involve inequalities. When there is inequality in the constant equation, we call them non-holonomic. So gas molecules moving in a closed spherical vessel with its center at origin is, in this case, motion of the particle is restricted, but non-holonomic equations is not providing us definite relation between x, y, z. So it is inequality involved, but not a definite relation. Means you can't reduce the variables from here, because you don't have a fixed relation between x, y, z. You are just having that this distance should be less than equal to r square. So in non-holonomic, we don't have definite relation. Due to this nature of constant equation, one cannot reduce number of required independent variables to describe the motion of the system. As we were able to reduce the variables here in the holonomic constant, we are not able to reduce in the non-holonomic. and this kind of it may involve non-integrable velocity components. In this non-holonomic, we have this kind of components of velocity which which are non-integrable, means you can't convert them to the holonomic form, and they involve this kind of things, x dot, y dot, z dot, which is non-integrable. So this was the examples and the definitions of integrable and means holonomic and the non-holonomic constants. Now what were the problems due to these constants, means this was the part I have to introduce before. Let me introduce here. So what were the problems was faced due to constants? So we have to introduce these Lagrangian. What was the problems? So there were two problems. Due to constant relations, coordinates are no longer independent of each other. See, as we have the free motion, then x, y, z components are independent of each other. Means the motion, if something is moving, then its motion is independent of x, motion is independent of y, y is independent of z. But with the constant relations, means there are constant relations, then x will be dependent on the y and y will be depending on the x. So the coordinates are no longer independent of each other. So we cannot solve the problem just by resolving the motion in three orthogonal motions. Now we can't just resolve them and solve the equations because they are depending on each other. Later on, this problem was reduced by introducing generalized coordinates. So this problem will be reduced, means will be eliminated by introducing generalized coordinate. We will study about them. What are they in the Lagrangian? These constants are involving constant forces. This was the second problem. These constants are involving constant forces whose exact nature is not known to us. So because of these constants, we have these unknown forces of whose exact nature we don't know. So it was difficult to solve equations of motion. So now we can't solve the equation of motion because of this. I already told you this. This was the forces whose nature we don't know. So we can't solve the equations because the number of variables are more than the number of equations available. So later on, this problem was solved by the introducing energy techniques, which we call the Lagrangian and the Hamiltonian formulations. So that's how we solve them, because now we remove the forces and we introduce the energy terms. And this was the approaches which was Lagrangian and the Hamiltonian formulations. So that's it for today. In the next lecture, we will study that how many independent axes or independent coordinates we require, and that will be depending on the degree of freedom. Then we will see what are degree of freedoms and what are generalized coordinates. So we'll go more in detail then. So today, let's end here. Thank you everyone.